April 11, 1945, Kohnstein Tunnels, Mittelwerk, near Nordhausen, Germany. Flashlights sweep across raw rock and concrete. The air smells of cold stone, oil, and scorched paint. American ordnance officers step over rails sunk into the floor and stacks of crates stenciled with numbers in neat black Gothic script. In the beam of a lieutenant's lamp, a fin assembly leans against a timber. The paint is a checkerboard. The metal is thin as a blade. Major Robert L. Staver, chief of the Jet Propulsion Section, Army Ordnance, stops at a bulbous nose cone resting on a pallet. He runs his hand over the edge and feels the seam. He has seen the photographs of craters in London. He has read British estimates of trajectory and speed. He knows the acronyms and the code names, A4, V-2, Peenemünde, but this is the first time he can touch the machine itself. He traces a line from the nose to the barrel of the tank, down to the bell of the engine, and the black slabs of graphite jammed into the throat like a sacrificial altar. He kneels to the injector plate, presses a fingertip against one of the tiny orifices, and begins doing sums in his head, flow rate, chamber pressure, burn time, until the numbers all point to the same simple conclusion. "We are years behind this," he says quietly. Outside the mountain, on the hillside above Nordhausen, soldiers from the 3rd Armored and 104th Infantry Divisions have found Dora Mittelbau. The barracks, the faces, the hospital ward stacked with bodies, the gallows inside a tunnel. The shock is not only technical, it is moral. The weapon in the tunnel was built with hands that were starved, beaten, and worked to death. The American teams have two tasks at once: understand the machine and understand the cost. The weapon itself had been public for months, if only in its effects. On September 8, 1944, at 6:44 p.m., the first operational V-2 struck Staveley Road in Chiswick, West London. There was no warning, no engine note. A deep thump, a column of dust and shattered brick, and then the delayed thunder of the supersonic shock arriving after the impact. That same day, a V-2 struck near Paris. The British mapped the arcs, measured the craters, and listened to the pattern. The name for the German A4, Vergeltungswaffe 2, the V-2, was propaganda, but the physics behind it was not. A ballistic missile had entered the war. The program that built it began years earlier at Peenemünde on the Baltic coast. In October 1942, A4 V-2 No. 3 completed the first fully successful test flight, a short burn to an apogee near 84 to 90 kilometers. "We have invaded space with our rocket," General Walter Dornberger told his team at Karlshagen. "We have proved rocket propulsion is possible for space travel." It was more than a boast. It was an engineering milestone, a pump-fed, liquid-fueled rocket large and reliable enough to be mass-produced. The RAF's Operation Hydra raid in August 1943 struck Peenemünde hard, killing key personnel and revealing to German planners that the facility could not be protected. Production moved underground to the Mittelwerk, dug into the Kohnstein mountain near Nordhausen. The labor was supplied by prisoners from the Dora Mittelbau concentration camp. Approximately 60,000 were forced to work there. At least 20,000 died from starvation, disease, beatings, hangings, and accidents. The number of people killed building the V-2 exceeded the number killed by the V-2's impacts, a grim arithmetic that every Allied technical officer carried with him into those tunnels. By April 1945, American units had overrun the Kohnstein entrances. What they found was a factory and a supply chain. Jigs, fixtures, engine sections, guidance packages in padded crates, pumps, valves, and stacks of sheet metal waiting to be rolled into tank sections. It was, in American eyes, less a laboratory than a production line. Colonel Holger N. Toftoy, an ordnance officer who had followed German rocket developments since before the war, moved quickly. He and Major Staver organized Special Mission V-2, locate, secure, and ship as many let V-2 parts and documents as possible out of Nordhausen before the Soviets, whose front line was pushing in from the east, claimed the region under Allied agreements. Railcars were loaded with crates of components. In total, enough parts to assemble roughly 100 V-2s were gathered, shipped to Antwerp, then across the Atlantic to New Orleans, then by rail to the American Southwest. The second race began simultaneously, and it had names. On May 2nd, 1945, Werner von Braun, technical director at Peenemünde, his mentor Dornberger, and a core group of engineers including Eberhard Rees, Ernst Stuhlinger, Konrad Dannenberg, and others surrendered to American forces near Reute, Austria. Von Braun's left arm was in a cast from a recent car crash. He and his colleagues had decided they preferred American custody to Soviet. They brought lists of colleagues and an implicit bargain, their knowledge in exchange for safety and employment. The American response took two forms. One was logistical. White Sands Proving Ground was carved out of New Mexico desert scrub, and a temporary technical headquarters was established at Fort Bliss, Texas. Project Hermes, managed by General Electric for the Army Ordnance Department, would instrument, assemble, and launch captured V-2s as experimental platforms. The second was bureaucratic. Operation Overcast, soon renamed Operation Paperclip. Paperclips attached to the dossiers of selected German engineers signaled expedited processing. Military necessity trumped politics. The Joint Intelligence Objectives Agency narrowed security questions to enable hundreds of German specialists and their families, ultimately more than 1,600 people over the program's life, to relocate to the United States. Across the occupation zones, the same calculus played out in reverse. The Soviets had captured Peenemünde itself. They gathered what hardware remained, recruited German rocket specialists led by Helmut Grottrup, and reassembled the technology at institutes around Moscow and on Gorodomlya Island. Under the chief designer Sergei Korolev, the Soviet Union would fly the R-1, a copy of the V-2, by 1948. Korolev would then iterate R-2, R-5, and ultimately the R-7 Semyorka, the world's first intercontinental ballistic missile and the launcher of Sputnik in 1957. Britain moved quickly to document the weapon in full. Under Operation Backfire in October 1945, Royal Engineers supervised German crews who assembled and launched 3 V-2s from Cuxhaven as Allied observers took notes and photographs of every step: tools, fueling sequences, wiring harnesses, temperature management, and crew drills. The official reports were blunt. This was a new category of weapon, beyond interception by contemporary means. The American conclusion after the first walk through the tunnels and the first weeks of handling crates was equally blunt. The V-2 was not a prototype. It was a product. Outside, the V-2 looked simple: a steel cylinder tapering to a pointed nose, 4 wedge-shaped fins at the base. Inside, it was everything American field engineers weren't building in 1944. Large, high-flow liquid propulsion, an inertial guidance system, a thin-shelled structure engineered to survive both the violence of launch and the high-speed buffet of transonic flight, and a field logistics doctrine that made mobile launch practical. The A4 V-2 stood roughly 14 meters tall, with a diameter of about 1.65 meters and a fin span of approximately 3.56 meters. Fully fueled, it weighed about 12.5 metric tons, of which roughly 8.7 to 9.0 tons were propellant, liquid oxygen as oxidizer, and a 75% ethyl alcohol's 25% water mixture as fuel. Its warhead carried around 975 kilograms of amytal in a steel casing. At liftoff, the engine produced approximately 245 kilonewtons of thrust, equal to about 25 metric tons force. Burn time was roughly 60 to 65 seconds. The missile accelerated through the sound barrier seconds after clearing the launch platform, past max Q, the point of maximum dynamic pressure, while still under power, and approached Mach 3 to Mach 3.5 near the end of the burn. On a typical operational trajectory, it reached peak altitudes in the 80 to 90 kilometer range and traveled about 320 kilometers. Vertical test shots could go higher, brushing what we now call space. Numbers that matter to engineers told the real story. An engine that could maintain stable combustion at these thrust levels required a mass flow of propellant on the order of 125 kilograms per second. That meant pumps, lines, valves, injectors, and cooling passages all working together with minimal room for error. The V-2 did that, repeatedly, under field conditions. American teams had experience with small rockets. Robert H. Goddard had pioneered liquid-fueled flight in 1926 and demonstrated gyroscopic stabilization, gimbaled thrust, and regenerative cooling in the 1930s. The Guggenheim Aeronautical Laboratory at Caltech, GEL, was building small-sounding rockets and jet-assisted takeoff units in wartime. But nothing in the American inventory matched the scale of the A4. The V-2's engine was a single, circular combustion chamber fed by a steam-driven turbopump. The steam came from a separate generator where concentrated hydrogen peroxide decomposed over a catalyst to produce superheated steam and oxygen. That steam spun a turbine connected to two centrifugal pumps, one for liquid oxygen, one for the alcohol-water mix. The choice of fuel blend was deliberate. Pure ethanol burns hot. Adding water moderated combustion temperatures, reduced coking, and protected chamber walls. Before injection, the fuel circulated through channels in the chamber jacket, absorbing heat, regenerative cooling, before entering the injector. The result was a chamber that could run for a full minute without melting, a remarkable feat with 1940s alloys and machining. The injector plate, the metal disc at the top of the chamber, looked like a shower head, but with more than 1,000 tiny orifices, each carefully sized. The job of the injector was to atomize the fuel and oxidizer into a fine mist and mix them evenly. Poor mixing leads to hot spots and pressure oscillations that can couple with the chamber's acoustic modes. That is how rocket engines tear themselves apart, often in milliseconds. V-2 engineers solved this with injector geometry, mixture ratio tuning, and chamber shape. They didn't have high-speed digital sensors, but they had experience. Thousands of static firings and full-scale tests, many of them at Peenemunde's Test Stand 7, had taught them what worked. The gargoyle-like plates thrust into the exhaust, graphite jet vanes, were the next shock. In the first seconds of flight, before the fins had enough airspeed to bite, the missile's direction was controlled by servo-driven shafts that lowered thick slabs of graphite into the exhaust stream. Graphite, a form of carbon, can survive very high temperatures without melting and without catalyzing the propellant mix. American and British engineers had talked about jet vanes in theory. The V-2 teams had done it in practice, reliably enough to trust in combat. A V-2 did not rely on a radio beam for navigation in normal operations. It carried its brain inside a compact compartment packed with gyros, accelerometers, amplifiers, and a mixing unit labeled Mischgerät. Companies like Askania and Kreiselgeräte built the gyroscopes. Siemens manufactured servos and electronics. The autopilot had three principal jobs. The first was to hold attitude. Gyroscopes sensed rotation in pitch and yaw. An analog circuit fed commands to actuators on the jet vanes and, later in flight, to the fins. The second was to control the timing of engine shutdown. A longitudinal accelerometer integrated acceleration to produce a velocity signal. When the integrated velocity reached a predetermined value, the target cutoff velocity necessary to hit the range, the system commanded propellant valves closed. The Germans called it Brennschluss. The third was to avoid oscillation. Control gains had to be tuned so the system was responsive without hunting, harmful pilot-induced oscillation in a pilotless machine. This self-contained inertial guidance was revolutionary in a service weapon. It meant a V-2 could be fired from a clearing in a forest without a fixed radio infrastructure. The price was accuracy. Circular error probable was measured in kilometers. As a terror weapon against cities, that was enough. As a precision weapon against point targets, it was not. The V-2's skin and frames were built to be just strong enough. Tanks were thin to save mass. Welds had to hold at cryogenic temperatures for liquid oxygen and at ambient fuel temperatures during slosh and thrust. The structure had to survive the transonic shock and buffet as the missile punched through the sound barrier while still under power. Fins provided static stability and minimal control authority at speed. The primary control surfaces remained the jet vanes, which did not care about air density and continued to work into the thin air of ascent. Perhaps the most modern thing about the V-2 was not a specific component, but the way all the components were integrated into an operational doctrine. A V-2 battery traveled with a convoy. The Milowagen transporter erector served as the launch table. The Vidalwagen low loader carried the missile by rail and road. Fuel and oxidizer came in separate trucks, the ethanol mix in standard tankers, the liquid oxygen in insulated cryogenic tanks with boil-off valves. Hydrogen peroxide arrived in drums. Power trailers brought generators. A small forest clearing could be turned into a launch site. A standard crew could level the Mailerwagen, raise the missile to vertical, connect the umbilicals, pre-cool and purge lines, fuel both propellants and the peroxide, check continuity, arm the warhead, and count down to launch in a few hours. After launch, the site could be cleared and the unit moved within 90 minutes. No Allied country had fielded anything like that by 1944. The United States had impressive engineering talent and a mature manufacturing sector, but its rockets were either small, experimental, or solid-fueled adjuncts to aircraft. In thrust, the difference is stark. The early American Whack Corporal's engine produced on the order of 6 to 7 kilonewtons. A V-2 produced roughly 245 kilonewtons, more than 30 times as much. American programs were just beginning to tackle pump-fed engines at scale. The V-2 was already using them in combat. Between September 1944 and March 1945, German forces launched more than 3,000 V-2s, primarily at London and Antwerp, with other targets in Belgium, France, and the Netherlands. In London alone, approximately 2,700 people were killed by V-2 strikes and more than 6,000 injured. Total deaths across all V-2 targets are commonly estimated in the range of 7,000 to 9,000. By contrast, at least 20,000 slave laborers died producing the missile underground at Middlework. The weapon was technologically advanced. It was also morally contaminated by the conditions of its manufacture. The British adapted by attacking the program's periphery. The August 1943 raid on Peenemünde forced production underground. Polish Home Army units recovered V-2 parts from test crashes near Blizna and smuggled components across occupied territory in 1944, an operation known as Wildhorn 3, to British intelligence, who used them to infer design details. Bombing focused on fuel plants, depots, and transport nodes. Anti-aircraft guns and fighter patrols could not stop a supersonic ballistic weapon. The only viable defense against a V-2 in 1944 was to prevent it from being launched. The United States received shipments of V-2 parts through the summer and fall of 1945. At White Sands Proving Ground in New Mexico, Army Ordnance and General Electric assembled the missiles like kit aircraft, mixing German and American hardware to make up for missing parts. The goal was not to weaponize them, it was to learn. Project Hermes launched its first V-2 in April 1946. Many flights failed, engines exploded, guidance went hard over, turbopump seals leaked, telemetry cut out, but other flights reached the fought edge of space. On October 24, 1946, a V-2 carried a 35mm motion picture camera into the high atmosphere and returned the first photographs of Earth from near space, the curvature of the planet visible across black sky. The film canister was ejected and floated down under a parachute, recovered by jeeps racing across the desert. Navy researchers in the Naval Research Laboratory used V-2s as sounding rockets for physics and atmospheric science, taking measurements that were previously impossible. The bumper program, conceived by the Army and carried out with JPL and General Electric, stacked a small American upper stage, the Whack Corporal, on top of a V-2. The idea was both simple and radical. Use the V-2 to lift the Whack into thin air at high speed, then light the second stage to reach altitudes no single stage could. Bumper 5 reached roughly 244 miles, about 393 kilometers, on June 24, 1949, setting an altitude record. Bumper 8, launched on July 24, 1950, became the first rocket launched from Cape Canaveral, Florida, establishing the range whose name would become shorthand for American spaceflight. White Sands also taught methodology. Checklists were written and rewritten. LOX boil-off rates were measured at specific ambient temperatures, leading to better insulating blankets and tighter countdowns. Valve sequencing was timed to the second. Electrical continuity checks were repeated, then documented in triplicate. Telemetry stations rehearsed as rigorously as infantry drills. Range safety protocols, the authority to terminate a flight that strayed off its corridor, were established and enforced. Engineers learned to think in ascent profiles, gimbal rates, and cutoff logic. This procedural discipline, as much as any specific component, was the V-2's most immediate gift to American rocketry. Operation Paperclip's first group of German specialists arrived in the United States in late 1945. They were housed at Fort Bliss, worked at White Sands, and reported to American officers. Von Braun led the engineering group. Dornberger, as a senior Wehrmacht officer, was held for longer. Arthur Rudolph, who had supervised production at Middlework and would later manage Saturn V's first stage program. Kurt Debus, an electrical engineer who would eventually become the first director of NASA's Kennedy Space Center, joined launch operations. Eberhard Rees, Konrad Dannenberg, and Ernst Stuhlinger formed the Propulsion and Guidance Corps. Their expertise dovetailed with American capabilities. North American Aviation created an engine division, Rocketdyne, to design and produce large liquid-fueled engines. The Redstone missile, developed by the Army Ballistic Missile Agency at Redstone Arsenal in Huntsville, Alabama, used a Rocketdyne engine derived from the V-2 lineage, but improved in every performance metric: higher thrust, improved injector and cooling design, better reliability. The Redstone became the booster that, with a Mercury capsule on top, launched America's first astronaut, Alan Shepard, on a suborbital flight in May 1961. Before that, the Jupiter IRBM and its modified cousin, the Jupiter C, were tested and used as launch vehicles. On January 31, 1958, a Juno I, a Jupiter C outfitted with a lightweight fourth stage, lofted Explorer 1, America's first satellite. James Van Allen's instruments on board discovered a belt of high-energy particles encircling Earth, the radiation zone that bears his name. The data began in the V-2's guidance compartment, in how to protect electronics from vibration, heat, and vacuum during ascent. On the other side of the Iron Curtain, Sergei Korolev treated the V-2 as a training tool, not an end state. The Soviets built and flew the R-1 by 1948 and quickly improved it. By 1957, the R-7 could lift a sizable payload into orbit. When Sputnik beeped over American skies on October 4, 1957, the message required no translation. The Soviet Union had a booster that could place an object into orbit, which meant it could throw a warhead across continents. The V-2 had shown what was possible. The R-7 had shown what was done. American responses split between the Navy's Vanguard program, civilian, scientific, and plagued by early failures, and the Army's AMA team in Huntsville, which leveraged a proven engine line and a production organization to place Explorer 1 in orbit. The policy argument resolved with the creation of the National Aeronautics and Space Administration in 1958. 2 years later, the Army's Development Operations Division, von Braun's team and its test stands, transferred to NASA as the Marshall Space Flight Center. From that point, the scale changed. The Saturn I and Saturn IB tested clustering of tanks and engines. The Saturn V drew a new line in propulsion. Its first stage used 5 Rocketdyne F1 engines, each producing roughly 6.77 meganewtons of thrust, nearly 30 times the thrust of a V-2 engine. The cooling channels, turbopumps and injector plates were orders of magnitude more complex, but the core vocabulary had not changed. Pump-fed LOX and fuel, regenerative cooling, injector stability, gimbaled thrust, inertial guidance, countdown discipline. The road from A4 to Saturn V was not direct, but it was traceable through people, processes, and physical laws. The first dividing line was turbomachinery at scale. Pumping cryogenic oxidizer and ambient fuel at a combined mass flow above 100 kilograms per second for over a minute without cavitation, seal failure, or catastrophic vibration requires precision in impeller design, seal materials, bearing lubrication, and shaft dynamics. It also requires a start sequence that brings the turbine to speed and meter flows in the correct order. The V-2's hydrogen peroxide steam generator, concentrated peroxide decomposed over a catalyst, made that possible with a compact, rugged power source. American teams extracted and replicated that logic, then moved to more energetic propellant combinations in the 1950s. First LOX and kerosene, RP1, then LOX and liquid hydrogen for upper stages. The second dividing line was combustion stability. At large chamber diameters, acoustic modes can resonate and cause chugging or screech, pressure oscillations that, if coupled with injector spray patterns, can destroy the engine. The V-2's engineers learned to avoid these regions through testing and injector baffle designs. That knowledge became a starting point for American injector science. When Rocketdyne struggled with F1 combustion instability in the early 1960s, the test program, bomb tests to perturb the chamber, redesigned injector baffles, and instrumentation that listened for the onset of instability, echoed V-2 lessons scaled up by an order of magnitude. The third dividing line was inertial guidance. Holding attitude with gyros and steering with servo-controlled vanes at the end of a long, flexible structure is not trivial. Control laws must account for bending modes, time delays, and sensor drift. The V-2's analog autopilot, based on gyros and an integrating accelerometer, introduced engineers to a new class of problems that would grow in the 1950s and 1960s. At MIT's instrumentation laboratory, stable platform inertial systems replaced spinning gyros and pendulous accelerometers, driving accuracy from kilometers to hundreds of meters, and then to the precision required for lunar flight. Wrapped around those dividing lines was the concept of systems engineering. A V-2 launch battery acted like a small factory on wheels, with supply, operations, quality control, and safety all integrated into a routine. American officers in 1946 realized that's what they needed. Not a brilliant engine alone, but an organization that could fuel, test, instrument, and fly it every week on a schedule. What American scientists and soldiers learned in those tunnels in April 1945 was less a single secret than a set of habits. The V-2 was a map: where to spend money, what kinds of technicians to train, which failure modes to watch for, and which ethical problems demanded daylight instead of secrecy. The consequences ran in three directions at once: war, peace, and memory. For war, the V-2 taught the hard limits of defense. In 1944, there was no way to shoot down a ballistic missile in flight. That fact hardened into Cold War doctrine. Intercepting a re-entry vehicle remained impractical for decades. Deterrence, the decision to prevent launch rather than catch the weapon mid-arc, became the center of strategy. Meanwhile, the V-2's field doctrine, mobile erector launchers, rapid setup, concealed fueling, foreshadowed the road-mobile missiles that would define much of the later nuclear standoff. For peace, the V-2 opened the atmosphere. Sounding rockets carried cameras and instruments into regions of sky where weather balloons burst and aircraft could not fly. The first photo of Earth from space came back on curled film stock ejected from a nose cone that fell onto New Mexico sand. Instruments measured ozone density, cosmic rays, and solar ultraviolet. They returned data that shaped meteorology, space physics, and communications engineering. The multi-stage principle tested by Bumper became the core of orbital flight. Every modern launch traces back to that logic. For memory, the V-2 came with a ledger. The middlework and Dora Middlebow were not footnotes. They were integral to the rocket's existence. American officers walked out of the tunnels and into the spring light at Nordhausen with two images pressed together: the beauty of a solved engineering problem and the horror of how it was manufactured. Operation Paperclip tried to untangle the two by moving the people and the knowledge into a new national project, but the tangle never fully disappeared. Von Braun, Debus, Rudolph, Dannenberg, and others became central figures in American rocketry. Their technical contributions were undeniable. Their pasts were complicated. Public memory retains both truths at once. The Saturn V flew, and Dora existed. The lesson that American engineers repeated in internal memos and training programs was blunt, because it had to be. The gap existed because the United States had not invested as a state in large liquid-fueled rockets during the crisis years of 1940 to 1944. Robert Goddard had many of the right ideas, protected by patents and proven with small test stands, but without an institutional customer with a wartime mandate and budget, those ideas did not become 1,000 engines in a rail yard full of crates. Germany, for reasons both strategic and propagandistic, made that investment. The Allied response after 1945 was to build the missing institutions: test ranges, engine manufacturers, guidance laboratories, and a civil space agency that could justify steady funding. The time from years behind in a tunnel to a lunar landing in July 1969 was 24 years. That is the kind of speed only possible when knowledge is paired to organization and will. There is also a smaller, more personal legacy, almost quiet next to the power of the missiles. Engineers in the White Sands blockhouses learned to say no-go without apology. A valve that didn't close to spec, a telemetry channel that didn't lock, a leak rate that exceeded the line, those became launch-stopping conditions. It was a new culture for a military accustomed to improvisation. It grew directly out of the hard lessons of the V-2. Rockets are intolerant of wishful thinking. They will punish haste. A checklist is not bureaucracy, it is survival. Return to the opening scene. Staver and the officers in Middlework that April carried two kinds of clarity out of the mountain. The first was an engineering inventory: thrust levels, burn times, injector plate geometry, mass flow, guidance logic. The second was a story about what it takes to build such a machine. Factories, trained crews, test stands that run all day, logbooks filled with data, and an administrative shield big enough to make mistakes and learn from them. Within months, crates from Nordhausen sat in New Mexico sunlight. Within a year, American crews were launching captured rockets over white sands and chasing parachutes with jeeps. Within a decade, American rockets were lifting satellites into orbit. In 2 decades, a 5-stage vehicle assembled by a team that included paperclip alumni and American graduates of new university programs stood on a pad in Florida, 250,000 miles of trajectory penciled into the guidance computer. The ethical shadow never disappeared, and it should not. It belongs in any honest telling, and an honest telling acknowledges both the debt and the cost. "We have invaded space with our rocket," Dornberger said in 1942. The line reads differently when you remember where the later rockets were built and by whom. The American program that followed attached a different set of values to the same equations: open inspections, public funding, civil agency oversight. When the engines lit at Canaveral, it was in front of cameras, not behind a mountain. The final implication is the one Major Staver understood before he stood up from that injector plate. If you are behind, the only way forward is to admit it, inventory what you lack, and build the institutions that will close the distance. The V-2 did not hand the United States a space program. It handed the United States an agenda: learn turbomachinery, master combustion stability, develop inertial guidance, institute systems engineering, and hold to a culture that treats a launch as a test you must pass rather than a stunt you can bluff. The United States did those things with speed and scale, powered by a Cold War that made rockets both weapons and symbols. The story resolves in a pair of dates. April 1945, in a tunnel in Germany, the bottom of a learning curve. July 20th, 1969, at Tranquility Base, the top of a different one. Between them run thousands of test firings, dozens of White Sands launches, Operation Backfire at Cuxhaven, paperclip train schedules, Bumper at the Cape, Explorer 1's beeps, the creation of NASA, and stacks of technical reports where engineers taught themselves how to push liquid through metal at frightening speeds without everything exploding. American scientists examined a German V-2 rocket and realized they were years behind. They were right. Then they closed the gap the only way anyone ever does, with numbers, procedures, questions that turn into better tests, and a memory of what not to become. The lesson is not that technology erases its origins. It is that a society can decide what its technology is for and how it will be made, and in whose name it will fly.